In Part 19, the focus was on oxidation numbers. This presentation expands on the concept of oxidation numbers, as they are used in redox titrations. The focus here is on what redox reactions are, and how are they balanced. It is information that is used in redox titrations, as well as electrochemical analysis. I am Rob Boyko, Boyko Mineral Exploration, and welcome back. In most chemical reactions that involve a compound or compounds, there will be more than a single reaction that takes place. The standard reduction potentials table is built on this concept. Take, for example, nickel-3 hydroxide being dissolved in hydrochloric acid. The first reaction is the dissociation of the nickel hydroxide, that's the nickel-3 hydroxide. The second reaction is the dissociation of the hydrochloric acid. We also have the combining of the ions to form products, and at equilibrium there will be the opposite reactions forming the reactants, and so on. The reactants will remain in solution as ion molecules in equilibrium, while others form analyte ions. In the first reaction, the nickel-3 hydroxide dissociates into nickel-3 elemental ions and polyatomic hydroxide ions. The second reaction is the dissociation of the hydrochloric acid dissociating into elemental hydrogen ions and elemental chlorine ions. As the nickel dissociates from the hydroxide, 3 negative charges are lost from the molecule, or can be considered as donated. The nickel is said to be reduced to elemental solid nickel, as the nickel is insoluble in hydroxides. This is a half-cell reaction. The nickel-3, having an oxidation number of +3, is now reduced to having an oxidation number of 0, a pure solid crystallized element. In other words, a half-cell reaction is either reducing or it is oxidizing. For redox reactions that must have a balanced reaction equation, there are some simple rules that need to be remembered. The ion charge, that is, the oxidation number, must be determined, and the number of electrons, that is, the E-, that are transferred must be shown. The E- charge is always added to the higher oxidized state. Now, as shown with the half reaction, the stable elemental zinc donated 2 electrons to become elemental zinc 2 ions in an aqueous solution. The elemental silver, having a +1 oxidation state, receives an electron to become a stable elemental silver ion in a solution. This would be the half reaction for the silver. If both were in the same solution, a balanced reaction equation would need to be shown, showing the molarity of the ions in solution. The product side is the other half reaction at equilibrium. The red line depicts the center of the 2 half reactions. The zinc shows that 2 electrons were transferred, that is, donated, resulting in the zinc 2 ion. This is an oxidation reaction. Also shown, the silver 1 ion receives, that is, it accepts a single electron, resulting in a stable silver ion in solution. This is a reduction reaction. What needs to be noted is that the number of electrons for each half reaction has to be equal. Since there were 2 electrons transferred from the zinc, then there must be 2 electrons added to the silver as shown. Since there are 2 electrons added to the silver, and the silver ion only accepts 1 electron, then there must be 2 silver ions in solution. By process of elimination, the E- can be cancelled out. By adding up what is left over on the reactant side, we get 1 zinc ion and 2 silver ions. On the product side, we do the same thing. What needs to be noted here is the ion charges must be equal in the final balanced equation. The zinc in the solution reacted with the silver in the solution. Silver ions are more reactive than the zinc and want to be stable. The zinc, being less reactive, gave up 2 electrons, and 2 silver ions take on, that is, accept, the 2 electrons, which form the 2 stable silver ions. The second example here shows the reaction of magnesium and iron 2 in the same solution. The red bar divides the two half reactions. Since 2 electrons were transferred in each of the half reactions, by simply canceling out the 2 E- charges, we get the balanced equation as shown. Notice that this example is a little different, as the oxidation numbers for the elements are not 1 to 1 or 2 to 1, but in a 3 to 2 ratio. The copper and the aluminum charges need to be balanced. The 3 E- charge does not equal the 2 E- charge. In order to balance the charges, the aluminum will have to be multiplied by 2, and the copper will need to be multiplied by 3. The result is a 6 E- charge for both the copper and the aluminum ions. Since the E- charges were increased, the number of copper and aluminum ions had to be increased accordingly. As shown, the E- charges were cancelled out. The balanced equation is as shown. The balanced charges are also shown and underlined in red. This is an example of an acid-base redox reaction. In any acid-base reaction, water is created. In this example, 3 oxygen atoms are donated. The ratio becomes 3 to 2. Because 3 oxygen atoms were donated, 3 hydrogen atoms would have to be donated to create the water molecule. That means there must have been 3 electrons donated or a 3- charge. Now it takes 2 hydrogen atoms to create 1 molecule of water, or 2 electrons donated. Since we have a 3 to 2 ratio in E- charges, the next common multiple is 6. Therefore, the zinc 2 must be multiplied by 3, and the hydrogen must be multiplied by 2 to give us a balanced E- charge, which means that all the hydrogen must also be multiplied by 2, and the zinc multiplied by 3. As shown, the final equation is balanced. In this example, hypochlorite is being used along with the solid aluminum. It is still an acid-base reaction as oxygen atoms are donated during dissociation, and therefore water will be produced along with the aluminum chloride salt in an aqueous phase. Notice how the E- charges are not equal and must be accounted for as the solid aluminum oxidizes to aluminum 3 or aluminum 3 plus, and the hypochlorite reduces to chlorine minus. Therefore, all items in the aluminum oxidation equation is multiplied by 2 to obtain the least common multiple for both equations, which is 6. The hypochlorite reduction equation is thus multiplied by 3. The final balanced equation is as shown. This example with permanganate in solution and a pure iron solid, the dissociation of the two species is shown. This is similar to an acid-base reaction, as oxygen molecules are transferred, resulting in the formation of water. The balanced redox equation can be challenging for some. To start, the oxygen number for the manganese will need to be known. However, the molecule itself has a 1- charge. It is also the oxidation number for the molecule. Oxygen has 2- ion charges. 4 atoms in the molecule has a combined ion charge of 8- or 8- overall. Since the molecule has a 1- charge, the overall oxidation number is -8 minus the -1, which equals -7. Therefore, the oxidation number for the oxygen atoms combined is -7. Now this means that the oxidation number for the manganese ion will be +7. The oxidation numbers are thus equal to 0, therefore balanced. As shown, the +7 plus the -8 equals -1, or MnO4 minus. Knowing that the oxidation number for the manganese is +7, we can move on. The iron oxidizes to produce iron 3, with 3 electrons donated. The permanganate reduces to manganese 2, gaining 5 electrons, and water also produced. Note that the E- charges are not equal, and the manganese ion in the reaction has an oxidation number of +7, which reduces to +2. The common multiple between the two reactions is 15, thus must be accounted for in the final balanced equation. The iron reaction must be multiplied by 5 as shown, whereas the manganese reaction must be multiplied by 3. Canceling out the E charges, the E- charges that is, the final balanced equation is as shown. In this example, the dissociation reaction between the iron and the perchloric acid is shown. The iron oxidizes to iron 2, plus hydroxide, and 2 electrons are transferred. The perchlorate dissociates with the water in the solution, resulting in chlorine and hydroxide. Note that the electron transfer is added to the side with the most oxygen atoms. This is the reactant side. The electron transfers are cancelled out as well as the hydroxide ions, leaving the final balance equation in this oxidation reaction as shown. There are times that redox reactions become complex. The example of a dissociation reaction will not have equal charges. The number of iodine atoms will need to be increased for a balanced equation, as we have 3 iodine atoms in the product side. The chlorate dissociates and 6 electrons are used for oxidation. Note that the iodine must be multiplied by 2 to the next common multiple, which is 6. Therefore, the equation can be rewritten as shown, as well as the final balanced equation. In this reaction, the hydroxide will dissociate. Since the sulfide is aqueous, as it dissociates and reacts with the water, hydroxide is formed. Water, being the H+, will need to be added to the product side. The nickel 3 reduces to nickel 1, with an oxidation number of 0. 2 electrons are transferred. The E- charges and the hydroxides cancel, but note that there will be 1 hydroxide ion left over after the OH- is cancelled out. 3 minus 2 equals 1. The balanced equation is shown. Well, this is the last example for this part of the series, part 20. The water in the magnesium solution reacts with the magnesium, forming magnesium hydroxide. The chromate reacts with the water for chromium hydroxide. The E- charges are not equal and must be multiplied to the next common multiple, which is 6. As shown, the equations are then rewritten. Note that the hydroxides are cancelled out. However, there are 10 hydroxide ions associated with the chromate and 6 associated with the magnesium. After cancelling the 6 hydroxide ions out, 4 are left over in the product side. The final balanced equation is as shown. In part 19 of this series, the discussion was on oxidation numbers. It was the starting point for redox reaction equations and the balancing of these equations. This is important knowledge for those that wish to conduct electrochemical analysis and refining. In part 21, which will be published soon, I have decided to focus on some electrochemical analysis before going into other methods of titration, not yet discussed. I hope that this will entice you into viewing Part 21 when published. If you found this presentation of benefit, or you know of someone who may benefit from this presentation, please give it a like and a share. It's my only reward. I am Rob Boyko, Boyko Mineral Exploration, and I thank you for watching.